Yeah. So in this video we will see we'll continue about knife based classifier. Okay. The basic introduction of knife based classifier is explained in another video, and the link of that video is given in the description here. Okay, in this video. So here this is Bayes theorem, and we had one data set. Okay, so here we looked into these three terminologies in the previous video. If you have not seen that video, first go through that video and then come back to this so that you will have more clarity of what we are discussing about. Okay, so this is prior probability. So now if the data set is given, what is this prior probability is? Prior probability is equal to yes or probability of P is equal to no. Okay, so prior probability is computed for classes of the data set. So in this data set we have two classes, yes and no. Okay, so for that we are computing, and we have 5 samples overall. Among the 5 samples, 2 samples are having yes class and 3 samples are having no class. So this is the prior probability of yes class and no class. Okay. Because the prior probability of how to compute prior probability we have seen given the data set. Okay, then this is actually a likelihood. Okay, and mathematically we call this likelihood is a joint probability. So here we know that A represents the sample. What do you mean by sample? Here this is one sample, this is one sample, yes1 here. So for yes1 sample has feature A1 value as A11, feature A2 value as A21, feature A3 value as A32. Okay, so the sample means it has feature values. Okay, here also if this joint probability, if we wanted to compute, what we are supposed to do is we have to calculate it for A1, A2. This is nothing but this one. Okay, this is joint probability. To calculate this one, what we are supposed to do is A1, probability of A1 given A2, A3 and class value into probability of A2 value given A1 value, A3 value and class value into probability of A3 given A1, A2 class value. Okay, to compute this one we are supposed to compute these three. Okay, so here what happens is if we consider this probability value, let us see. To compute the probability of A1, first we have to look at the scenario of A2 value and A3 value. Here A1 is depending on A2 and A3. A2 here is depending on A1 and A3 in this computation. Here A3 is depending on A1 and A2. Okay, so here the attribute, the features are depending, one feature is depending on other features, right? So that was actual calculation, but the term knife, so till now we have seen the Bayes theorem. So now we'll look into the term knife. Okay, knife means, it means why we consider the word knife is because here it is representing features are independent. There is no dependency between the features. No one feature is dependent on the other feature. There is no relation between two features. That's what the main point here knife means. Why we wanted to take this? Actual calculation is that there is some dependency. if we actually wanted to calculate this probabilities, there is some dependency definitely. But then we are considering, we are taking an assumption that there is no dependency. Why? The reason why we wanted to take there is no dependency is this computation is costlier. Okay, if we don't have, if we don't consider the dependency, how we are going to calculate? We simply calculate A1 given B class, A2 given B class, and A3 given B class. This computation is simpler than this computation, because here A2 unique values will be there, A3 unique values will be there. Okay, here we are having less computational cost compared to these computations. If we don't consider the dependencies, this is what we are going to calculate. If we consider the dependencies, this is how we are supposed to calculate. But in naive Bayes, we are assuming that there is no dependency. So we are going to do this one. We are going to calculate this one. So now in naive Bayes, how we are going to calculate A given B is probability of A1 given B into probability of A2 given B into probability of A3 given B and prior probability of B. That part is already there in the Bayes theorem, but here computing likelihood or joint probability, this is how we are going to compute. This is how we are going to compute. So there is no dependency. To avoid the computational cost, okay, to avoid the computational cost, at the same time, we also need to find the relation between the label and feature. That's the reason why we are considering this dependency. That's the reason why we are considering this one, this dependence. We are how the attribute or the feature values are dependent, how dependent, how they are related to the class label that we are looking into. Okay, that relation is being captured with even with this equation, that even if we consider that there is no relation between the features, there is no dependency between the features, but still we can find the relation between the feature and the label. Feature and the label. Okay. Moreover, if there is some sparse data, for example, if you see here, let me see one combination which we don't have. Here you see, consider A22 and A31. In this data set, this combination is not there for attribute A2 and A3. Okay. Because this combination is not there, so this combination is like you can't get this combination, right? When you can't get this combination, and if you are trying to calculate here for the same combination, this probability will become 0. Okay. Or else, if you are having a very huge data, suppose you are having 100 samples, not only 5, but still there is no such combination, or you have only one among the 100 samples have this combination, then your probability value will be very, very, very less, right? So it means that the data sparsity, the rare combinations will make the overall, the rare combinations is going to make the variations in the overall computations, right? So to avoid such things and to have the relation, to avoid such probability, small probability values, and to have relation between feature and class label, we are going with naive Bayes classification. So we are using Bayes theorem only still, but we are computing this considering that there is no dependency between the features. So that's the reason why we call this classifier as naive Bayes classifier. Here I wanted to clarify one more point, that no features are independent, they are not dependent on each other, independent. Okay, at the same time all features are equally important, are equally important, because here we are not considering that a feature A1 is more important than feature A3. There is no such point. We are considering that all the features are equally important and all the features are independent of other features, and we are trying to find the relation, how the features are affecting the label, that we are trying to consider, that we are trying to find. Okay, so that's why we call this as naive Bayes. So now it is clear that to compute this probability of A1 given B, probability of A2 given B, if you are having suppose n number of attributes, so this will be the overall naive Bayes classifier probability computation. Okay. Now, in our explanation, we focused on this term, on this term, on this term more and more. What about this one? Why we are not much focusing on? That is because if we want to calculate for two classes, for example, probability of B is equal to yes class and A1 given yes class, probability of A2 for some value given yes class, probability of A3 given yes class by even into probability of yes class, prior probability, and probability of A. A means nothing but A1, A2, A3. Okay. So now if we want to calculate the same for no class also, then how we will calculate the same thing for no class, probability of A2 given no class, probability of A3 given no class, probability of no class by probability of A1, A2, A3. See, here when we are computing this for yes class and no class, the denominator value is same. Okay, the denominator value is same. When the denominator value is same, then can we conclude the prediction of label by considering only the numerator? Is it possible? Let us look into this point. Is it possible to conclude the label? Is it possible to predict the label with only the numerator without computing this evidence? This we call it as evidence, which is marginal probability. Okay. So without calculating this, is it possible? If possible, how it is possible? Please comment down in this video. Okay. So with this, we have introduced the basics of naive Bayes, what is and how to calculate, what's the difference between these probabilities and all. So now in the next video, we will try to solve a problem. We will consider a data set and we'll try to predict the label of one sample by using this naive Bayes classifier. Okay. So your next questions in this video will be how to train naive Bayes. Classifier. What are you supposed to do? Okay. And your second question will be what if the unique value of an attribute is not present in the data set. I hope I don't know whether you understood this question or not. Let me explain the question clearly so that you can think of that question. Unique value of the attribute is not present. Okay, here you are having the data set. Okay, so you can calculate the probabilities for the values that are present in the data set. For example, in case if a new value comes, for example, I wish to have something called A13 for attribute A1. Okay, so in this data set there is no A13. This value is not present in the data set with attribute within the attribute A1. So can we calculate its probability? If we calculate, what will be the output? What is that probability and how to calculate that probability, or what happens? Think about this, and in the coming video we will look at the examples how to solve Naive Bayes. Okay, thank you.